Now suppose we have a slightly more complicated setting where maybe there is one cluster with one element, and then there is another cluster that has two elements, and then there is another cluster that has three elements, all the way up to a cluster that has about root n elements. And that distances within cluster elements are very small, and distances of elements within different clusters is 1. Now the calculation we did before is not working anymore, because suppose that we're looking at elements of two different clusters. And suppose that we are looking at the distribution where a random element of V is picked, and then we form A to be just that singleton. Then, especially when we're looking at two different small clusters, almost surely this random element will belong to neither of them. So then FAV will be 1, FAV will be 1, and the difference will be 0, while it should be 1. And if we pick A uniformly at random, there is going to be very high probability that A intersects both the cluster of U and the cluster of V. And again, this will cause the difference between FUA and FVA to be about 1 over n, which is off by a factor of n from the actual distance, which is 1. So this shows that we need some distribution of sets that has some good probability of hitting one cluster but not the other, so that FA will be 0 or 1 over n for one of the vertices, and it will be 1 for the other vertex. But since here we're looking at sets that have basically all possible sizes, how can we guarantee that the set A is going to hit one set and not the other? The average intersection between A and that set should be a constant or more. But also, to have some good probability of avoiding a set, the average size of the intersection of A with the other set should be also a constant or something going to 0. So we cannot balance anymore between the case of A having average size 1 and average size n over 2, and then hoping that one of those two cases will work. It seems that we need to balance A between having all possible average sizes. So it seems we could say, well, we're going to pick some size t uniformly at random between 1 and say n over 2, and then we're going to pick A to be a random set of size t. Now this is still not going to work, because if I look at two small sets, there are only going to be very few values of t for which we get reasonably good probability of hitting one set and not the other. Once t is such that the average intersection size of A with the sets goes, say, beyond log n or below 1 over log n, then the probability of actually having an intersection with one and not the other will become very, very small. So the range of t for which we might hope for things to work is just a range of log square values of t out of n. So it's a very small range. The contribution to the expectation will be very small. So what Bourgain does in general, and what you have to do even in a relatively simple example like this, is to mix several distributions of set sizes, but not mix them with all the sizes being equally likely, but just by having a few representative sizes being considered. So the following approach works. We are going to pick t uniformly at random from the set 1, 2, 4, 2 to the log n. So there are only going to be log n choices. And then we pick a random A of size t. And in fact, it will be more convenient to think about the process in the following alternative form, where what we pick randomly is what fraction of elements will belong to A. Alright, now let's say we have these two clusters, let's say S1 and S2, with S2 being the bigger. Then we expect the intersection of A with S2 to be of size S2 over T on average, and the intersection of A with S1 to be of size S1 over T on average. So when T is about S2, this will give us a constant expected intersection for S2 and constant or smaller expected intersection for S1. So there will be a constant probability that we hit some element of S2 and some constant probability that we avoid S1. So there will be some constant probability for the choice of T that FAV will be very small and FAU will be 1. So at least for that value of T, we get a contribution to the expectation, which is a constant. We have only log n values of T, so we get that the expectation is going to be at least 1 over log n. So this case contains almost all the difficulties of the general case, although it's simpler than the general case in one way, which is that here there is always, for every 2 vertices, some choice of T, such that if we pick a random set A of size n over T, we are getting an expectation of FAU minus FAV, which is within a constant factor of the distance of U and V. The reason why we lose a factor of log n, it's because the right choice of T only happens with probability 1 over log n. In a final example that we consider, even this property will not be true, although that distribution over A will still work. So again, let's say that we pick a parameter T to be a random power of 2, and then we choose a set A randomly of size n over T. It will be easier to reason about it if actually we think more or less equivalently of A as being defined so that each possible vertex is chosen to be included in A with probability 1 over T. So first we make a random choice of T to be between roughly 1 and n, but there are only log n possibilities. And then we pick A by selecting independently each element to be or not be in A, with the probability of being in A being 1 over T. That's the 2-step process by which the set A is sampled. Now let's say that we have a graph in which every vertex has constant degree, but every cycle has length at least some constant times log n. In fact, the issue that we will describe comes up even in a simpler graph like this, which is just 2 binary trees joined at the leaves, even though this graph has small cycles. Although when we look at this vertex U and this vertex V, those are vertices such that up to half log n distance from them, we don't see any cycle. Now suppose a set A is chosen randomly in this way. And now we wonder what's going to be the expectation over A of FAU minus FAV. Well, once a parameter T is chosen randomly, we're going to have an extremely high probability that the closest vertex to V is going to be within distance log T plus or minus some constant from V. Because when you go to distance log T plus some very large constant, the number of vertices that you're looking at is T times some huge constant. And so the expected number of elements of A that you would see in there is some huge constant. And the probability of not seeing any element of A would be very small. And when you look at distance log T minus a large constant, you're looking at the number of elements which is roughly T times a very small constant. The probability of seeing any element of A in there is going to be very small. So except with very small probability, the closest element of A to V will be a distance log t plus or minus, say, 100. And the same for V. So except with some tiny probability, the difference between FAU and FAV is going to be a constant. And actually, if we work out how the probability of this difference being larger decreases, we can establish that this difference in expectation is, for every choice of t, at least some absolute constant and at most some absolute constant. And so it will also be a constant when t is chosen randomly according to this distribution. And this satisfies Bourgain's theorem because the actual distance between u and v is constant times log n. However, it's not true anymore that this loss of log n comes from the fact that there is only one value of t that is good, and then for that value of t, the expectation over the choices of a, but for that fixed t, is within a constant factor of the true distance. Here what's happening is that for every choice of t, we have an error of 1 over log n. And so then we need to take into account the contribution to the expectation of all of the values of t to get this factor of log n. Otherwise, if we were focusing on only one value of t, we would be getting a loss of log n squared.